Hello everyone and welcome to Virtual Class 12. Today is Tuesday, May 12th. A few things that I want to mention right off the bat. Number one, the molar volume of hydrogen gas lab was due on Monday, May 11th. If you have not done so, please turn that in immediately. If you have any questions about the lab, please reach out through Schoology Messenger or using email. Second, the exam from last week on gas laws was graded and entered into the gradebook. If you did not receive a grade, or if you received a question about your test, please make sure to reply to that as soon as possible. Again, if you have any questions, please reach out. Today, we're going to continue with our thermochemistry unit. We have two important topics today: phase diagrams and heating curves. So we're going to jump right into this. I'm going to send this out to our resident scientist, Kevin, who's going to talk all about phase diagrams and what they mean. Take it away, Kevin.
Thanks, Kevin. All right, so I'm going to talk about phase diagrams, and if you look behind me here, I have two different examples of phase diagrams. I have a phase diagram for carbon dioxide and a phase diagram for water. What you're probably asking yourself is, what is a phase diagram? Well, basically, it's a map that tells you, depending on pressure and temperature conditions, whether something is going to exist as a solid, a liquid, or a gas. Same thing on this example for water, whether something exists as a solid, a liquid, or a gas. So let's use water as our example, and if you notice, I have a mark where 1 atmosphere would be. So that's where we are. We're at 1 atmosphere of pressure. So sometimes it's referred to as sea level. So if I draw this line across for 1 atmosphere, like so, I go from the solid phase to the liquid phase to the gaseous phase. Now, if I were to drop a line down to where temperature is in degrees Celsius, so I'll do that. We would be able to identify those temperatures. So for water, the temperature at which water changes from a solid to a liquid, we know that. That's 0 degrees Celsius. And the temperature at which water changes from a liquid to a gas, we also know, that is 100 degrees Celsius. And many of us used that when we were completing our exams last week. The same could be done for carbon dioxide. But think about this for a second. At 1 atmosphere, we experience all 3 phases of water. So we know water as solid, ice. We know water as a liquid, like when we turn on the faucet. And we've all boiled water, so we know water can turn into steam. So at 1 atmosphere, you're going to see all 3 phases of water. However, if you think about carbon dioxide, chances are you've probably never seen liquid carbon dioxide. And the reason for that is simple. Here we are at 1 atmosphere. If I draw this line for 1 atmosphere across, notice that carbon dioxide goes directly from the solid phase to the gaseous phase. So for some materials, depending on what they are, they might see all 3 phases, solid, liquid, gas, or they might see just 2. Now, could you get liquefied carbon dioxide? Absolutely. At any point in this section, you would have to increase the pressure and increase the temperature, but it would be possible to experience liquefied carbon dioxide. So what I would like to do now is to go through some of the terms. These are not new. You already know most, if not all, of these terms. And we'll do it first on water, but they apply to both water and to carbon dioxide. So the first term is called, going from solid into a liquid, it's called melting. And the opposite of melting, which would be going this direction, is called freezing. And going from liquid to a gas is called vaporization. Going from a gas back to a liquid is called condensation. Most likely you've heard of those terms before, and this is nothing new. Now, One of the terms that you may or may not have heard of is sublimation. So going from a solid directly to a gas is called sublimation. That's what carbon dioxide does, dry ice, when we leave it exposed to air. It sublimes. It undergoes this process of sublimation where it changes directly from a solid into a gas. What most students don't know is the opposite of that process. So this process, going from a gas directly to a solid, that's known as deposition. Now, we're probably familiar with watching dry ice change directly from a solid to a gas because that takes place at 1 atmosphere. Even though we probably have never seen it and perhaps never will, it is also possible for ice to sublime. However, you would have to reduce the pressure significantly and lower the temperature. So under normal conditions, water wouldn't sublime, but if you were to isolate it in a system where you're able to lower the pressure, it could. Now, I'm going to move on, and I'm going to talk about a couple of other important points on the graph, and the first is going to be right here. This point is called the triple point. So the triple point is the only place on the graph where you have a temperature and a pressure where all 3 phases of matter could coexist. So you could have solid, liquid, and gas all coexisting. Same thing on this graph for water. You have a triple point here where all 3 phases could coexist. I always get asked this question, what would a triple point look like? Well, it's not as great as you might think. So a triple point might just look like if you put an ice cube into a glass of water. So you would have the solid phase of the ice cube, you would have the water, liquid phase, and then above it, even though you couldn't see it, you have to believe that there's water vapor there. The difference would be at the triple point, it would be in equilibrium. So imagine putting an ice cube into a glass of water and having it remain an ice cube forever. That would be the difference. When we're not at equilibrium and we put an ice cube into water, the ice cube melts in order to obtain room temperature. So a subtle difference there. Now, we know that the 2 lines that I dropped down over here have names. So they are called, this is called the freezing point. When it occurs at 1 atmosphere, it's called the normal freezing point. And when it occurs between liquid and gas, it's called the normal boiling point. Now, seems weird to use the term normal, but the truth is that water can boil at a whole bunch of different temperatures if you adjust the pressure that you're at. So this entire line represents the transition from a liquid to a gas. So you could boil water at any temperature as long as you were able to lower the pressure enough. So if you want to see this, you could do this simple trick at home. So I have a regular old CVS syringe that we used to use to give like antibiotics to my children when they were younger. It's not a needle, it's a needleless syringe. It's not for injecting any type of medication. Now, if you were to hold it and cap it off, so I've filled the top part here with water, and I'm going to make sure that all of the air is outside of the syringe. So now, from this point where the stopper is to the top, I'm going to try and hold this correctly. All of that is filled with water and there's no air in there. When I pull down on the syringe, the pressure inside is going to be lower. And the reason is volume is going to go up, but air is not going to be able to fill into the syringe because I'm blocking off the top. So I'm going to lower the pressure by pulling down on this plunger. Now, according to my diagram, here we are at room temperature. So let's say room temperature is around 25 degrees Celsius. So we're sitting somewhere around here. if I lower the pressure enough, I should be able to boil water. So if I lower the pressure by increasing the volume, I'm going to travel right along this line, and I'm going to cross this point, which is the boiling point. Now, it won't be the normal boiling point because we're not at 1 atmosphere. However, I can make water boil at room temperature. So, don't believe me? Think about what water looks like when it starts to boil in a pot. You start to see little bubbles on the bottom, and those bubbles rise up. So I'm going to show you this. I'll turn it so that you could see it. Right now it's at standard pressure. If I lower the syringe down, you start to see the water boiling right there. And everyone always asks the same question. That's awesome. Does it feel hot? And I said, no, we didn't do anything to change the temperature. We were at the same temperature. We just lowered the pressure in the syringe enough that we were able to get water to boil. If you have a needleless syringe, this is completely safe to do at home. Just make sure that you fill it with just a little bit of water. So you notice in my case, I filled it with about 3 or 4 milliliters worth of water. Get all of the air out, cap it with your finger, and then pull down, and you too can make water boil right at room temperature. Now, we're going to send it back over to the desk so that we can go to our last segment, which is going through a heating curve. So it sounds similar to phase diagram, and it's sort of related, but it's a little different. So I'm going to send it over to the desk, to Kevin. He's going to talk about what we're going to do next. See ya.
Thanks, Kevin. That was a cool trick you showed there. All right, we're going to move on to our second segment, which is heating curves. Heating curves basically are a way to track how much energy is required to go between 2 different temperature points for a specific substance. Sometimes that point requires that you go through a phase change, and the process changes a little bit in those cases. So here to tell us about heating curves and how to calculate the amount of energy to go from one temperature to another is our staff scientist, Kevin, who is going to go through an example with you and let you know what the homework is. Take it away.
Thanks, Kevin. Okay, I'm back at the board to show you the difference between a heating curve and what we're going to talk about next, and the phase diagram that we had talked about a little earlier. Side note, look what I rescued. Oh, anyway. All right, so a heating curve is slightly different than a phase diagram. It provides different information. So this behind me is the heating curve for water. And I left this up here so that we could do a little comparison between the two of them, because sometimes I get confused. If I haven't done this in a while and someone says phase diagram or heating curve, I forget what they're talking about because they do have similar information. Now, if you're looking at the heating curve, the first thing that you'll notice is that the phases, just got really sunny there, the phases, solid, liquid, and gas, are kind of like sections, blocks, sort of like they were here. And these points are the cutoffs. So this would be the melting point, right? Going from a solid to a liquid. And this would be the vaporization point, going from a liquid to a gas. If you are trying to think about the difference between these two, this is occurring at a single pressure. So going across this heating curve is like traveling across this line right here that I have dotted this direction. It's like traveling across this line. So I start off with a solid, I add heat, so the temperature goes up. Then at this point, I go through a phase change. That phase change is stretched out a little bit here. You'll see why the phase change is stretched out in a heating curve. And then I continue going across, and then I go through another phase change. So you see that phase change right here in between liquid and gas. One of the most important things that you'll notice is energy is being added at a constant rate down here. So if you notice, when you're going through a phase change, energy is added, but that energy is not being used to raise the temperature anymore. So what is that energy being used for? When you're going through a phase change in a heating curve, the energy is actually being used to sever the bonds. So when we talk about water and going from a liquid to a gas, we know that water undergoes hydrogen bonding because it has hydrogen and a highly electronegative oxygen atom. So some of that energy that's being added is actually being used to separate those water molecules from each other. All right, what I'm going to do is I'm going to pause. I'm going to erase this diagram since I'm done with that comparison, and I'm going to write up the information for a sample problem that we're going to do together, and I'll be back in 1 second. Okay, I'm back. Had to adjust the lighting because blaring sun was coming in. Anyway, so what I have up here I want to go over. So if you look on the side here, first of all, I wrote available constants. When you're doing these heating curve problems, there are a ton of constants. And the crazy part is the constant is not only specific to the substance that you're talking about, it's also specific to the phase of matter that that substance is in. So if you notice, we're going to be dealing with the with a heating curve rather for water, and I have 3 different constants, one for water as a solid, one for water as a liquid, one for water as a gas, and furthermore, I have 2 other constants that we have to be aware of. So let's go take a look at our heating curve. What I want to do is to try and identify where each of these constants would be used. So the first thing, sorry about that. The first thing that you'll notice is that I have an equation here, Q equals mCp delta T. So obviously the Cp constants are going to be used in this equation. The other part of that equation that's important is the delta T part. So delta T, if you remember from our first video, means change in temperature. One of the homework problems, or a couple of them, kind of gave us some trouble because we got confused with Kelvin and Celsius and changing temperature and when to add 273 and when not to. Hopefully I explained that well enough on all of you that made that, explain that to all of you that made that mistake. So we're going to be using delta T here. The good news is we're not going to worry about converting to Kelvin. So for thermochemistry, we can actually leave most of our temperatures in Celsius, which I know is confusing just coming out of gas laws, but that's the way it is. So when we're using this equation, and I'm going to call this equation A, when we're using equation A, we can only use equation A on parts of the graph where the temperature is changing. So down here where the temperature is changing, we can use equation A. Here where the temperature is changing, we can use equation A. And here where the temperature is changing, we can use equation A. The reason why we can't use equation A in these 2 spots when it's going through a phase change is because temperature is not changing. So the change in temperature would be 0 and Q would end up equaling 0. So we needed another equation, an equation that allowed us to calculate, even when temperature was not changing, what that energy being added was actually doing. So we came up with this equation. The heat energy that's being added is dependent on the mass of the amount of substance. That makes sense. So more heat energy is going to be required to, let's say, boil 100 grams of water compared to 5 grams of water. So that part makes sense. And then another constant. So there are 2 delta H constants, the delta HF and the delta HV. So I'm going to first label this B. So we're going to say we use B here and we use B here. So we use that equation. And now let's take a look and label the constants. So I'm going to label these constants 1 through 5. So I'm going to start down here. For a change in temperature, so it's a Cp of a solid. So I'm going to call this constant number 1. Then when I'm coming across here, I'm going through a phase change. This F in delta H actually stands for fusion, but you could think of it like freezing. So this is my second constant. So I'm going to label this 1. This is my constant 2. Then I'm back into changing temperature again. So I'm going to use one of my CPs. This time I'm going to use the CP for it as a liquid. So I'm going to call that 3. We're going to write the 3 right up here. Then I go through another phase change. So again, I'm going to use equation B. This time, the V stands for vaporization, right? Going from a liquid to a gas. So this phase change is called vaporization. So in this part, I'm going to use constant 4. And then finally, for this, so let me label this 4 here. And then finally, for this last part, where we're increasing in temperature once again, we're going to use the last Cp constant, which I'm going to call number 5.
We'll call this number 5. Now, the way I'm going to teach you how to do this is going to utilize these numbers. So what I'm going to do is I'm going to move out of the way, and I want to just give you a second, hit pause on your video, make sure that you have this drawing down and that these spots are labeled. So you ready? Go. All right. So hopefully after hitting pause and hitting play again, you're back with me. So what we're going to do is we are going to look at a question together. So I'm going to put that question up right now. Magic. And what we're going to do in this question is we are going to look at the amount of energy required to take 25 grams, so 25.0 grams, this is our mass, and we want to change its temperature. So we want the temperature in this problem, this fictitious problem, to change from 80 degrees Celsius up to 118 degrees Celsius. Now, I just made up this problem. You could have problems that are longer, you could have problems that are shorter, you could have problems that are easier, you could have problems that are harder. So I just picked kind of a middle of the road problem for us to try together. So my first suggestion to you is on your heating curve, identify where you are at and where you are going. So I'm starting at 80 degrees Celsius. 80 degrees Celsius is somewhere right around here. This is my starting point. I'm finishing, if you notice, at 118 degrees Celsius. 118 degrees Celsius is way up here. So I'm going to just mark it off. Let's say it's right here, 118 degrees Celsius. So the next part that you have to do is decide, okay, based on my starting point and my ending point, how many different parts to this problem am I going to have? So the answer is 3. And here is where the 3 parts are coming in. I'm starting with liquid water at 80 degrees Celsius. So I need to first get that liquid water up to 100 degrees Celsius. So that's one step. Then I need to go at 100 degrees Celsius and go from all of that water being a liquid to all of that water being a gas. So that's part 2. And then I need to take that gas and heat it from 100 degrees Celsius, where I am here, up to 118 degrees Celsius. So I need to do this in 3 different parts. Now, it's possible that your starting temperature is way down here. In fact, on one of the homework problems, it is. On one of the homework problems, you're going to have a 5-part problem, which means you're going to have to start all the way down here and go up, phase change, up, phase change, and up again. But for the purpose of this video, I chose a shorter problem where we're only going to have 3 parts. So I'm going to start here at the starting line. So my first thing is the transition from 80 degrees Celsius up to 100 degrees Celsius. So we're going to use, since we're changing temperature, we're going to use the equation Q equals mCp delta T. My mass in all cases is 25 grams. That's another thing that's important to remember. When you're going through a phase change, the amount of matter is not changing. It might look very different. It might feel different. It might even feel like a different mass, but it's not. So if you have 25 grams of water, whether that water is a solid, a liquid, or a gas, the number of molecules that make it up is the same, and the mass of it is the same. So that's going to be a constant throughout our problem, no pun intended. The next part, I'm going to multiply that by the CP. So for this part, notice, I'm going to use the CP for number 3 because I have liquid water right now. So I'm going to multiply that by 4.184 joules per gram degrees Celsius. And the last part is my change in temperature. And this is where some students sort of get tricked. So I'm starting, remember, at 80 degrees Celsius. So my change in temperature is 80 up to 100. So a change in temperature of just 20 degrees Celsius. So I calculate what Q is, and magically I already have that done. So it's 2092 joules, but based on significant figures, it's just 2090 joules. We're going to say that it's 20.0. There we go. Good enough. So I just calculated this little piece. Now I'm going to do the next piece, which is at 100 degrees Celsius. So this time there is no change in temperature. I'm just going to mark this off so I know to save that. At 100 degrees Celsius, I'm going to use this formula, Q equals mass times delta H V. So here's the general formula. I'm using the delta H of vaporization because I'm going from a liquid to a gas. So you would put, if you were down here, you would put an F there instead. So in this case, I have 25.0 grams. I'm going to multiply that by my constant, delta HV, 2258 joules per gram. And this time I get an answer of 56,500 joules. Now, why does that make sense? Why is that temperature, or why is that energy, so much higher than the energy here? Think about what you're doing when you're vaporizing water. You're severing bonds and you're separating those molecules apart from each other. In fact, in a gas, they're very far apart from each other. So that's going to require a tremendous amount of energy. So don't be surprised if you wind up with Q values that are extremely high in one part of the problem and much lower in another part. So I have a Q value here, and I'm going to put a box around that one. The last part of this problem, and I'll do that over here, is going from 100 degrees Celsius up to 118 degrees Celsius. So 100 degrees Celsius up to 118 degrees Celsius. Q is equal to, because temperature is changing again, I'm going to use this equation, mCp delta T. My mass doesn't change, 25.0 grams. This time my Cp value is going to be different. Last time I used it for water as a liquid. Now I'm going to use it for water as a gas. So I'm going to use this constant, 2.01 joules per gram degrees Celsius. And now the last part is my change in temperature is 18.0 degrees Celsius. I multiply that out. I get an answer of 905 joules. Notice how the value for the Cp for water as a gas is lower than that for a liquid. It doesn't take as much energy to excite molecules of a gas as it does to excite molecules of a liquid, because liquid, they have to overcome these hydrogen bonds that they're making when they're really close to each other. In the gaseous form, those molecules are very far apart from each other, so it's easy to add energy to them and get a significant change in temperature. All right, now that I have all three parts, what I'm really trying to calculate is the total amount of energy. So I would take these three pieces, add them together. Notice that I have no decimal places, so I'm just going to literally add them and keep all the digits based on significant figures, and I get an answer of 59,495. So my final answer to this problem is the sum of all of these different parts added together. So again, couple of reminders. I'm going to talk about the homework in a second. Couple of reminders going forward. This is a three-part problem. You could have a one-part problem. You could have a problem that says, measure the amount of energy required to take water at 25 degrees Celsius up to 75. Well, 25 is here, 75 is here. That's only one part. So you would only need one equation, and your change in temperature would be 50 degrees Celsius. You could have one that goes from here to here and doesn't require you to go above 100. Or you could have any type of combination. The other thing that you could have is a decrease in temperature. The only difference is if there's a decrease in temperature, all of your Q values get a negative sign, because instead of absorbing energy, endothermic, you're releasing energy, exothermic. And we'll learn in our next class on Thursday that energy being released has a negative value, energy being absorbed has a positive value. So the only thing, and in fact, one of your homeworks is a downward curve. So one of your homeworks, your value for Q, I think it's the first problem, should be a negative number.
all of your Q values should be negative because temperature is decreasing and energy is being released. Your homework for tonight, homework problems 1 and 5. So only 2 parts. I believe homework problem number 1 has 3 parts and you're cooling, so your Q values are going to be negative. Homework problem number 5 has all 5 parts. I think you're starting at a temperature that's below 0 degrees Celsius and you're going all the way up. Homework problems can range from 5 parts, being the hardest, down to just 1 part. So imagine I gave you a homework problem that said how much energy is required to take 50 grams of water from 25 degrees Celsius up to 75. Well, 25 is here, 75 is here. That would be a 1-step problem. Anytime you go through a phase change, that's another step. Anytime you go beyond that, that's a 3rd step. Or in this case, if I were going all the way up, it would be 5 steps total. Alrighty, so please try the homework. If you have any questions, please use Schoology Messenger or email me. I've been trying to respond as quickly as I humanly can. And I'll also be around tomorrow for 2 Zoom sessions at 10 a.m. and 12 p.m. So if you have any questions, please let me know. All right, I'm going to send it back over to Kevin, who is going to close out the lesson for today. Thanks very much.
Thanks, Kevin. And that's all we have for today. So remember, your homework assignment is to complete problems 1 and problem number 5 on the heating curve homework, which is available on Schoology. Please, again, if you can, submit your assignment as a PDF because I can grade it much faster that way. And if you have any questions, please reach out through Schoology Messenger or through email. See everyone again on Thursday. Have a great week. Bye-bye.